Here we're going to have a look at 2006, question 4, part A. Now, at a glance, this little doozy looks deceptively simple, and part 1 is rather nice. Part 2, a little bit trickier. So, with all these questions, you've got to stop and think, what's our way to start them? Diagrams, then F equals ma. So, off we go. First of all, we have our two masses. This one is 0.4 kilograms, so it is, of course, having a downward force of 0.4 g and an upward force of the tension in the string. The other one is teeny bit bigger, 0.5, so it has a downward force 0.5 g and upward force of t. Okay, so stop and think, which way is it going to move? Remember, it doesn't matter if you're wrong once you're consistent, but this one we know is going to go down and that's going to go up. Okay, so that's all our cases. God, that is all of our directions sorted out. So, F equals ma. Well, we have t minus 0.4 g equals 0.4a. Okay, so of course a in that direction, a going down there. And going down, we have 0.5 g minus t equals 0.5a. Sometimes in marking schemes, you'll see them using f for the acceleration. I'd love to know why, but it doesn't really matter once we have a little constant to indicate it. Okay, so step 2, almost always the easiest way to deal with these is to do simultaneous equations because the t's cancel out. 0.4g, 0.4a. Goodbye t's. So we have 0.5g minus 0.4g, which is 0.1g, and that equals 0.9a. All right, we're looking for the accelerations, and that a is, of course, 0.1 or 0.9g. So we can say a is g over 9. That's one of those ones to write rather carefully because the g's and 9s, of course, is a disaster waiting to happen. However, we're all sorted out. We have our 9th g. Now, for the second part, part 2, we need to kind of think ourselves a little bit carefully. Okay, so we bring back the question here. It falls a meter, the big one hits the horizontal surface and stops. The string again becomes taut after t seconds. So you've got to think is what we have here is this one's going to go down, hit the surface, and this one is going to continue up and bounce back. All right, and it's that time going up and down before it goes up and stops and comes back again is our time. So if we think of this, okay, let's fix this page again. So what happens? 0.5 hits the ground, 0.4 goes up until gravity stops it, and then 0.4 goes down until the string is taut. Taut just means tight, so it's kind of gone, the tensions come back into it again. All right, well, what you might notice is that these two guys here are going to be the same time. Same time, also the same distance, but we're not really caring about distance so much in this one. So what we have here is we can call that time, if we go back and look at our question, I'm just going to bring my question back up here. There we go. We're going to go back and have a look at our question. They're going to use this as time t, as the total time up and down. So we're going to say that's a half t and a half t. Okay. Now that's going to make life a little bit easier. All right. So what do we need to figure out first? Well, it's going to go up until it stops and back down. So I think the first thing we're going to need to look at in this one is the speed we're going at this point. So we need to find v. What speed is 0.5 going when it hits the ground? All right, well, v is v, u was 0, acceleration was g over 9, writing carefully. The distance was 1, and the time is unknown. So, of course, these ones here means v squared equals u squared plus 2as. v squared is 0 squared plus 2 factor of g over 9 by s is 1. That's not so bad. So v squared is 2g over 9, which means v is the square root of 2g over 9. Okay, grand. So now we know how fast 0.5 was going when it hit the ground. That's how fast 0.4 is going once it's moving under just freely on its own. Okay, well, now we're going to figure out t. So actually strictly speaking, we're going to find half of t. Because I'm just going to look at this top piece here. It goes up until it stops. That's nice and easy. We know how fast it's starting out with. It's going to stop. It's going to be 0. We know there's gravity acting. This is a very nice standard little linear motion equation. So, as always, let's list them. Where speed v is 0, because that's when it stops. U is this v here, okay? The speed 0.5 is going when it hits the ground is the speed 0.4 is going when 0.5 hits the ground, because it's all one system. So that is a square root 2g over 9. I'm not going to work this out yet. Stuff might cancel. We'll see how it goes. What else have I got? The distance is unknown. The time is half t. And acceleration, I skipped that one there. Gone off our page slightly. So I'm going to squeeze acceleration in here. Acceleration is g. Okay. Now, which means as I'm looking at this one, my equation is going to be v equals u plus at. Okay. 0 square root of 2g over 9. Okay, now we got to watch our signs because it's going upwards with 2g over 9, so g is a negative minus g. And be careful here again, we're taking time as a half t. That's why I love writing these guys out here. It just stops all those little simple slips that can come in along the way. Okay, a little bit ugly. All we got to do is find for t. Now again, if you look at the question, find t correct to 2 decimal places. So we're not doing this in terms of g. We can begin to multiply this out. So what I'm going to get over here is root of 2g over 9 equals g over 2t. All right, well, let's go start figuring this stuff out. Square root of over 9, and that equals that delight there. 7 root 10 over 15, that's 4.9. You're getting used to it at this stage. So therefore t equals that divided by 4.9. Okay, I think we'll go to decimals at this point. T is 0.3 seconds. Oops, T has actually gone slightly off the camera, sorry about that. Therefore, T equals 0.3 seconds. And there's our answer there. Tricky question, but once you watch this and what's going on, the maths is nothing more than you'd encounter in an ordinary level question 1.